Foundation Module 9 UHS Modular Integrated Undergraduate Curriculum Physiology Dr. Sheen CEO and Founder Sheikh Zayed Medical College Physiology Department. Medical Superfast Simplified Physiology Video Lecture Notes. Guyton and Hall 14 edition chapter number 50 lecture number 1 page hashtag 627628 629 630. Physical Principles of Optics. Refraction of light. Refractive index of a transparent substance. Refraction of light rays at an interface between two media with different refractive indices. Application of refractive principles to lenses. Convex lens focuses light rays. Concave lens. Cylindrical lens bends light rays in only one plane. Comparison with spherical lenses. Combination of two cylindrical lenses at right angles equals a spherical lens. Focal length of a lens. Formation of an image by a convex lens. Measurement of the refractive power of a lens diopter. Optics of the eye. All refractive surfaces of the eye as a single lens. The reduced eye. Physical principles of optics. For understanding the optical system of the eye requires familiar with basic principles of optics. Physics of light refraction. Focusing. Depth of focus. Refraction of light. Refractive index of a transparent substance. Refraction is the bending of light rays at an angulated interface. Light rays travel through air at a velocity of about 300,000 km/second. Travel slowly through transparent solids and liquids. Refractive index of a transparent substance is the ratio of the velocity of light in the air to the velocity in the substance. The refractive index of air is 1.00. If light travels through a particular type of glass at a velocity of 200,000 km/second, the refractive index of this glass is 300,000 divided by 200,000 or 1.50. Concept of refractive index. This substance refractive index is 2. If any medium light speed is low and refractive index is bigger or high. Means in dense substance light speed is decreased and refractive index is increased, that is, speed of light is inversely proportional to refractive index. Refraction of light rays at an interface between two media with different refractive indices. When light rays traveling forward in a beam strike an interface that is perpendicular to the beam, the rays enter the second medium without bending. Decreased velocity of transmission and shorter wavelength. If the light rays pass through an angulated interface, the rays bend if the refractive indices of the two media are different from each other. The light rays leaving air, which has a refractive index of 1.00, and are entering a block of glass having a refractive index of 1.50. When the beam first strikes the angulated interface. The lower edge of the beam enters the glass ahead of the upper edge. The wave front in the upper portion of the beam continues to travel at a velocity of 300.000 km/second, whereas that which entered the glass travels at a velocity of 200,000 km/second. This difference in velocity causes the upper portion of the wave front to move before, ahead, the lower portion so that the wave front is not vertical but is angulated to the right. Because the direction in which light travels is always perpendicular to the plane of the wave front, the direction of travel of the light beam bends downward. The bending of light rays at an angulated interface is known as refraction. The degree of refraction increases as the 1. Ratio of the two refractive indices of the two transparent media. 2. The degree of angulation between the interface and the entering wave front. Points to be remember. Wavefront is a line or surface that is formed by joining all points of same phases. Or making a line on all crest and all trough. 0. Our wavefront is a surface joining points of wave which have same phase of vibration in the form of wavefront.v. Example: how water move from one place to another place. 2D wave of water. Wave of light can go each and every direction, it is sphere 3D wave. Application of refractive principles to lenses. Convex lens focuses light rays. The light rays, passing through the center of the lens, strike the lens perpendicular to the lens surface. Pass through the lens without refracted. The light rays strike both edge of the lens, upper and lower edge, more angulated. Outer rays bend more and more toward the center, called convergence of the rays. Half bending occurs in the lens, half when exit from the opposite side. Parallel light rays passing through each part of the lens will be bent enough so that all rays will pass through a single point, called the focal point. Concave lens diverges light rays. The rays that enter the center of the lens strike an interface that is perpendicular to the beam and do not refract. The rays at the edge of the lens enter the lens ahead of the rays in the center. It causes the peripheral light rays to diverge. Central rays not diverge. Cylindrical lens bends light rays in only one plane. Comparison with spherical lenses. Fig 50.4. Cylindrical lens is a type of lens with at least one surface that is curved into a cylindrical shape rather than a spherical shape. This means it has a different focal length in different directions. Focus light in one dimension. Parallel light rays are bent to a focal line. Cylindrical lens bends light rays from the two sides of the lens but not from the top or the bottom. Cylindrical lenses can be convex, positive, or concave, negative. A convex cylindrical lens converge light rays in one plane, positive focal length. Concave cylindrical lens will cause parallel light rays to diverge in one plane, have a negative focal length. Combination of two cylindrical lenses at right angles equals a spherical lens. Shows two convex cylindrical lenses at right angles to each other perform the same function as one spherical lens of the same refracted power. The vertical cylindrical lens converges the light rays that pass through the two sides of the lens, and the horizontal lens converges the top and bottom rays. All the light rays come to a single point focus. The combination of two cylindrical lenses focus uniformly in both the horizontal and vertical planes. Focal length of a lens. For a convex lens, the focal length is the distance from the lens to the focal point, where parallel rays of light converge. For a concave lens, diverging, it is the distance from the lens to the point from which parallel rays appear to diverge. In the middle diagram, the light rays that enter the convex lens are not parallel but are diverging outward from the point source. The bottom diagram shows light rays diverging toward a convex lens that has greater curvature than that of the other two lenses. The distance from the lens at which the light rays come to focus is same as that from the lens in the first diagram, in which the lens is less convex and entering rays are parallel. Note, both parallel and diverging rays can be focused at the same distance away from a lens, provided that the lens changes its convexity. Formation of an image by a convex lens. Convex lens with two-point sources of light to the left. Light rays pass through the center of a convex lens without refracted. The light rays from each point source of light come to a point focus on the opposite side of the lens in line with the point source and the center of the lens. This image is upside down with respect to the original object, and the two lateral sides of the image are reversed. The lens of a camera focuses images on film via this method. A convex lens can produce various types of images depending on the object's distance from the lens, with real images formed on the opposite side of the lens and virtual images on the same side as the object. Measurement of the refractive power of a lens diopter. The refractive power of a lens, measured in diopters, d, is a measure of how strongly the lens converges or diverges light. It is inverse relationship if power increase and focal length decrease. It is calculated using the focal length of the lens. 1 meter focal length equals 1 diopter. Focal length is distance between the lens and focal point or screen. The more a lens bends light rays, the greater is its refractive power. The refractive power in diopters of a convex lens is equal to 1 meter divided by its focal length. A spherical lens that converges parallel light to a focal point 1 meter beyond the lens has a refractive power of plus 1 diopter. 1 meter focal length equals 1 diopter. If the lens is bending parallel light rays twice, more than plus 1 diopter, it has a strength of plus 2 diopters, and a focal point 0.5 meter beyond the lens. A lens converging parallel light rays to a focal point only 10 centimeters, 0.10 meter. Beyond the lens has a refractive power of plus 10 diopters. Concave lens diverges light rays at the same rate and have a dioptric strength of -1. Likewise, if the concave lens diverges light rays as much as a +10 diopter lens converges them, this lens is said to have a strength of 10 diopters. Concave lenses neutralize the refractive power of convex lens. Note, placing a 1 diopter concave lens immediately in front of a 1 diopter convex lens results in a lens system with zero refractive power. The strength of cylindrical lenses are calculated in the same manner as the strength of spherical lenses. If a cylindrical lens focuses parallel light rays to a line focus 1 meter beyond the lens, it has a strength of +1 diopter. Conversely, if a cylindrical lens of a concave type diverges light rays as much as a +1 diopter. If the focused line is horizontal, its axis is said to be 0, 0 degrees. If it is vertical, its axis is 90 degree. Optics of the eye. The optics of the eye involve several structures that work together to focus light and create clear images. The lens system of the eye is composed of 4 refractive interfaces. 1. The interface between air and the anterior surface of the cornea. 2. Tahi interface between the posterior surface of the cornea and the aqueous humor. The interface between the aqueous humor and the anterior surface of the lens of the eye. The interface between the posterior surface of the lens and the vitreous humor. The internal index of air is 1.00. The cornea, 1.38. The aqueous humor, 1.33. The crystalline lens, 1.40. The vitreous humor, 1.34. All refractive surfaces of the eye as a single lens, the irreduced eye. If all the refractive surfaces of the eye are added together and then considered one single lens, the reduced eye model is a simplified representation of the human eye used in optics. Useful in simple calculations. The model simplifies the eye by assuming a single refractive surface rather than multiple surfaces: cornea, aqueous humor, lens, vitreous humor. It assumes a uniform refractive index for the entire optical medium of the eye. The eye's focusing power is represented by a single focal length. In the reduced eye, a single refractive surface is considered to exist, with its central point 17 mm in front of the retina and a total refractive power of 59 diopters when the lens is a common